Hello, this is Paul from Foresight Tech. In this video, let's prove Theorem 4.4.4. This theorem tells us how to determine the linear independence of a set of functions by using Wronskian. Okay, the set of function, let's say is S. Suppose this is S, and we only need to calculate the Wronskian, which is a kind of determinant of a matrix, okay, is not identically zero. If the Wronskian is not identically zero, and then we have a result. The set of S is linearly independent. What is Wronskian? Let me just put the definition here first for you. Okay, so this is the definition of Wronskian. What does it mean? This is a determinant of n by n matrix. The first row is the original function. The second row is the first derivative, and then the third row is the second derivative, and then goes to n minus 1's derivative. See, the condition says n minus 1's derivatives, they are continuous. Okay, so for the function, all these functions we have a good property. And then we calculate this Wronskian. If the Wronskian is a function, right? If the function is identically zero, means a constant function, it's not a zero, and then we will get a linearly independent. Okay, so we have to prove this. We have to prove when Wronskian is not zero, and then a linearly independent. Why? Okay. But before we prove this result, so let me give you a remark. And we can prove if Wronskian is not zero, and then linearly independent. How about the other case? If Wronskian is zero, okay, do you think we get a linearly dependent? No, it is not. Okay, so we cannot get any results. I'll put it the result here. Simply say if the Wronskian is zero, identically zero, which is a zero constant function, no conclusion we can get. It means either linearly independent or linearly dependent. Both are possible. Okay, so this is important. Now, let's go to the theorem how to prove if Wronskian is not a zero. How to get a linearly independent? We can use proof by contradiction. If not linearly independent, therefore linearly dependent, and then we will get a contradiction. It will contradict to the Wronskian, not a zero. We will get the Wronskian is zero. Or in another language, I can say this. So we only need to prove this. If linearly dependent, and then we will find a Wronskian should be zero. Okay, it's the same, right? So here the same. It just says a proof by contradiction. If not linearly independent, that's a linearly independent, linearly dependent. If linearly dependent, we get a contradiction. So therefore, it should be linearly independent. Why now? This is much easier. Okay, if linearly dependent, then by the definition means at least one function is a linear combination of the other. And start from here, we will calculate the determinant. Okay, is zero. See, linearly dependent, and then okay, so one function, one vector here, right, is a linear combination of the others. And let's say the first function, okay, f1 is a linear combination of the others. Let's say f1 is a linear combination of the others. So I directly get, so f1 it should be linear combination, right? Okay, so this F1 is linear combination of all the other, and then what do we get? See, look at this determined F1 is linear combination, and the F prime is also linear combination of the other first derivative, and then each derivative is also a linear combination of the others. And therefore, we will find that the first column should be a linear combination of all the other columns. So let me just put it here. Okay, this is true, right? But the linear property of a derivative. And then again, if I take the second derivative, and it is also true, the third derivative or the other derivative. So let's simply say this: any I derivative, okay, should be equal this. Okay, and from this, we definitely will find that the first column is a linear combination of all the other columns, right? Let's see. Therefore, we will get this. Okay, so the first column of the Wronskian is a linear combination of the other columns. Of course, it's true for all the x. Okay, for all the x in the domain. What does this mean? By the property of determinant, if we have one column is a linear combination of all the other columns, therefore by column operation, we will make the first column all zero, right? Okay, so, and then we can use the cofactor expansion, and the determinant should be zero. See, easy. So by some property we learned in chapter 2, okay. So the Wronskian should be zero identically. This is a constant function, which is a constant function. What does this mean? And this means a contradiction. See, we already find it, right? So we find a contradiction, which is the Wronskian is zero. The Wronskian contradiction means linearly independent, linearly dependent is not true. Therefore, it's linearly independent. Okay, so that should be the proof. Thank you.